Okay, so for the rest of the class today, I'd like to talk about the uh, abundance of planets that are similar to the Earth in that they're rocky planets, the abundance of the elements that we think are essential for life: carbon, hydrogen, nitrogen, oxygen, phosphor, and sulfur. At least the life as we know it here on Earth, and the abundance of water. And I'm going to start with the last point here, the abundance of water, because I think that's a less obvious. We're going to see that there are lots of rocky planets, and there are these elements are quite common. I think these are points that are a little bit easier to convince you, and then the abundance of water seem more important to me. So I'm going to start there. And in fact, this video will just be about the search for water in the cosmos. And I'm using this book by Onkranaz as a main reference, and also this website from of a satellite mission by ESA to study water in the universe. And here's an outline of what we'll talk about in this part of the class. We'll talk about the importance of water for life as we know it here on Earth, the importance of or the presence of water in the solar system. And then I'll talk about the search for water beyond our solar system. And so we'll go into some theory about how water is formed. We'll talk about the detection of water, because we're talking about detecting something that's thousands of light years away, or millions or even billions of light years away. How on earth do you do that? Well, I have to give you some background on the spectroscopy. And then we'll finally get to some of the results from this satellite mission by the European Space Agency called ESO, or ISO, looking for water beyond the solar system. Okay, so why do we say life is important, or water is important for life? Well, as always, we are limited to water as we know it here on Earth, but at least for water here on Earth, water has been important for the appearance of life, the development of life, and the maintenance of life. Water is by far the main constituent of living organisms here on Earth, whether they're animal or vegetable or even microorganisms. Turns out water is present everywhere in the universe. Unfortunately, we only observe it in the liquid, or pardon me, in the gaseous or solid states, but we think life needs water in the liquid form. So that's an important caveat in our study of water in the cosmos, is that we're limited to the detection of solid water, so ice, and gaseous water, so water vapor. It's the temperature and pressure, of course, that determine whether water is in which physical state. And these properties are not directly observable. So it makes it hard to confirm that liquid water is abundant in the universe, but we can at least determine that water is abundant in the solid and the gaseous forms. So then we can also extrapolate then that if a rocky planet forms that's at the correct temperature and pressure for water to be in liquid form, then you probably will have liquid water on that exoplanet, even if we can't detect the liquid water with our current technologies. So for the rest of this video, I'm going to talk about the formation of water, its abundance in the universe, and how do we know that it's present everywhere in the universe, at least in solid and vapor form. Well, in our solar system, there's liquid water in one of the moons of Jupiter. The moon Europa has a large ocean with liquid water. It's covered by a layer of ice, but under this layer of ice is a liquid ocean with liquid water. On Mars, there's evidence that water flowed on the surface of the Mars, on the surface of Mars. Today, there is water on Mars, but it's in solid form in the polar regions. There's ice on comets, and there's also ice in the rings around Saturn. So lots of water in the solar system. What about water outside of the solar system? Let's start first that discussion with how you could possibly form water beyond the solar system. So water has the chemical formula H2O. So it's built from hydrogen atoms and oxygen atoms, obviously. We've said that hydrogen is the most abundant atom or element in the universe. Among all the ordinary matter, hydrogen is the most abundant because it was created during the Big Bang. There was helium produced during the Big Bang as well, and it represents a little bit less than 1/4 of the ordinary matter. Of the 1 or 2% of the remaining elements, these are what we're going to refer to as the heavier elements, and they were mostly produced within stars. Among these heavier elements, oxygen is the most abundant. As a general rule, as a rule of thumb, the lighter the element, the more abundant it is, or the heavier an element is, the less abundant it is, because the lighter ones take less energy to produce by nuclear fusion. So here's a figure that shows the logarithm of the relative abundance on the vertical axis versus the atomic number on the horizontal axis. There's not all the elements, we just go out to atomic number 30 something here. But yeah, zinc is atomic number 30. But we've, so I took this figure from the book by Oncronaz. I've also adapted it a little bit by writing the atomic number for some of the key elements. Hydrogen is 1, helium is atomic number 2, carbon 6, nitrogen 7, oxygen 8, and iron is 26. So you could in principle read this off the axis here, but it's a little hard to read. There's atomic number 20, atomic number 30, and iron here is shown in red because it's atomic number 26. So hydrogen is the most abundant element, and helium is next, representing about 98% of the mass of ordinary matter in the universe, as we've said before. After that, oxygen, as I've just claimed, is the third most abundant element. Here's oxygen here, atomic number 8. It's a little hard to read, but oxygen's the next highest one. I guess it's, so that's the most important message from this figure, is that we have lots of hydrogen, we have large amounts of oxygen, so we have the building blocks of water. But since we've learned a little bit of astrophysics, it's nice to use that to try and understand this figure a little bit more. As I've already mentioned, hydrogen was formed in the Big Bang, so its abundance is the highest here, and in fact, it was by far the largest element produced during the Big Bang. The next, after helium, there's lithium, beryllium, and boron. These three elements were produced during the Big Bang in minute trace amounts. And so it might be a little bit surprising that they have such low relative abundance here relative to carbon, atomic number 6 here. But the reason for that we've already seen in that, remember when we followed the life cycle of our sun, and we said that currently it's converting hydrogen to helium. It's in what we call the main sequence of its life. But in approximately 5 billion years from now, the sun will increase its inner core pressure and therefore temperature sufficient to reach about 100 million degrees, at which point hydrogen will start, helium will fuse to form carbon in this triple alpha chain that we looked at. And so this, and in fact, we said that the helium inside the sun that 5 billion years from now is going to be converted into carbon in a few seconds. It's in what's called the helium flash. Remember, it's a big dramatic event that takes place in the interior of a star like our sun. during this red giant phase. So that explains the large production of or large relative abundance of carbon here, sort of bypassing these lithium, beryllium, and boron. You might, if you really remember the details, you might remember that beryllium was an intermediate step in the triple alpha process of converting helium to carbon. Remember, we had two helium nuclei coming together to form a beryllium-8 nuclei, but then that was quickly converted into a carbon nuclei with the addition of another helium nucleus. So that explains, this triple alpha process explains why the relatively large abundance of carbon. I guess it's also, I haven't explained the production of oxygen. There are many, it's inside the cores of stars like this at even higher temperatures. We can't really go into all the astrophysical processes happening inside of stars. It's nuclear fusion inside stars that is creating all these elements up to iron. We did mention that you can produce elements up to iron inside stars. It takes a star more massive than our sun, but you can generate all these elements up to atomic number 26, corresponding to iron. But why the peak here in the iron relative abundance? Because iron is a sort of bottleneck. That's the iron nucleus is the most stable of all the nuclei, and so that's the heaviest element that you produce inside the stars, and as a result you have a relatively large amount of iron given its heavy atomic number here, or large atomic number. To produce these heavier elements, zinc and these other ones with higher atomic number than 26, you need other processes. It's the supernova explosion at the end of the life of a massive star that creates these, or that's one important process for generating these elements heavier than iron. There are also collisions of neutron stars is another important process for generating the heavy elements. Okay, so we have the building blocks. We have the hydrogen, we have the oxygen to make water in fairly large quantities. But to form a water molecule, you need a chemical reaction, right? To join the hydrogen and the oxygen together. This is a chemical reaction. It's not the sort of, remember, it's nuclear reactions that are happening inside the stars. Now we're talking about a chemical reaction, the joining of a hydrogen atom, or in fact, two hydrogen atoms to one oxygen atom. So it's a chemical reaction. And this will take place in the interstellar medium, we believe, for as I'm going to explain. So the interstellar medium consists of about 99% gas, and the remaining 1% is dust of these elements that we just looked at. The temperature of this medium inside a galaxy, but between the stars, so the interstellar medium within a galaxy, is typically around tens of Kelvin, so less than 100 Kelvin. Remember, Kelvin is the absolute temperature scale. So if we're at 100 Kelvin, we're at minus 173.15 degrees Celsius. So it's cold. It's very cold. And so chemical reactions can take place, but they have to be chemical reactions that are exothermic. That means they are going to generate energy and release energy as they take place. Fortunately for the production of water molecules, this chemical reaction to produce water from 2 hydrogens and an oxygen is an exothermic reaction. So how does it take place? I'll show you just some of the steps. First, let me mention that the pressure in interstellar space is extremely low. It's a strong vacuum, right? It's easier to express it in terms of the number of atoms or molecules per centimeter cubed is about 1 atom or molecule for each centimeter cube in interstellar space, so between the stars, but within a galaxy. At these cold temperatures, at these low pressures, oxygen and hydrogen are in the gaseous form, they're gases. Hydrogen can be ionized by, it needs a collision with a particle like a cosmic ray. I haven't spoken of the cosmic rays yet, but cosmic rays are particles streaming through space at very high energy. They're traveling near the speed of light, and these particles can collide with hydrogen. There are cosmic rays here on Earth, by the way. They pass, many of them are blocked by the atmosphere, but some of them reach the surface of the Earth and they just pass right through our bodies. And they do, for the biologists, they do cause double strand breaks in the DNA. This is more of a concern for people who work in airplanes than the rest of us who spend most of our time near the surface of the Earth, because there are more cosmic rays higher in the atmosphere. And if you spend a lot of your time up high, then cosmic rays can have a health effect. They're also important in the production of water. Getting back to our sheep, as you say in French. So you have hydrogen plus a cosmic ray can lead to a hydrogen ion. So the electron this is the electron here, got stripped from the hydrogen nucleus, and the cosmic ray, it just continues on its way. They have more than enough energy to do this because they're, as I say, they're traveling near the speed of light. So it's very easy to strip this electron off. So then we have a proton, basically a hydrogen nucleus, which is positively charged, floating around in the interstellar medium. And there's oxygen around, because oxygen is an relatively abundant atom. And so this hydrogen, now we're getting into the chemistry, this hydrogen ion reacts with the oxygen atom to form the OH positive charge here, which I've written symbolically as this. So this hydrogen ion plus an oxygen atom react chemically to produce this OH ion. And now there are many steps in the chemical reaction that can lead this OH ion to react with an atom, a hydrogen atom, or even a hydrogen molecule. And this will lead to a water molecule being produced. You'll need a free electron, but we have free electrons buzzing around because they've been produced in this reaction 1 here. So here again in symbolic form is the chemical reaction written, where the OH plus ion plus another hydrogen atom plus a free electron produce the hydrogen molecule, releasing some energy. So this can take place at the low temperature, tens of Kelvin and low pressure that you find in the interstellar space. So we're producing water vapor. Even though it's so cold, it'll be water vapor because remember the pressure is essentially a very good vacuum. It's just 1 particle per centimeter cubed. I should mention that you can also form ice water, so solid water, in the interstellar medium as well. This happens in the following way. In the interstellar medium, you also have clouds of molecules which are a little bit more dense. It's still a strong vacuum, but you have these clouds where things are a little bit denser and still very cold, tens of kelvins here, and at most 100 Kelvin. And you can then form ice directly through a chemical reaction taking place on the surface of the dust particles. The dust particles serve as little reaction sites where the little grains of this to start this chemical or on the surface of which form the chemical reactions. Okay, so we have the building blocks to form water. We have the hydrogen and the oxygen. We understand the chemistry of how this can happen, even in the extreme conditions of interstellar space. How we should be able to see this water, the result of these reactions, the water vapor or the solid water. How would we see it when it's light years away from us? Well, through the light emitted by stars and passing through this medium. And how would that work? Well, we have to back up a little bit and talk about spectroscopy. And this will allow us to talk about how the astronomers tell the composition of anything they're looking at. They use spectroscopy to tell the composition of stars or galaxies or nebula or whatever they're studying. A spectral analysis is basically looking at the light and the intensity of light as a function of the wavelength of the light. Remember, light can be understood as a wave, and so it has a wavelength, and the different wavelengths correspond to, physically, they correspond to different colors. Whoops. And it turns out that every atom and every molecule has its own characteristic spectrum. Its spectrum both in the light that it absorbs and the light that it emits. And when I use the word light here, for the translation of the French lumière, usually we think of light in the visible part of the spectrum, light we can see. But light, of course, also comes in the ultraviolet and the infrared wavelengths as well. And because there are literally dozens of these emission and absorption lines associated with each molecule and atom, they form a sort of, that are unique to the atom or molecule in question. They form a sort of digital fingerprint, if you like. They allow us to identify the presence of different atoms and molecules based on the effects they have on the absorption of the light. And to really appreciate how the notion of spectroscopy and how it allows you to identify these atoms and molecules, it's good to just look at an example of a particular spectrum. So here I have the emission spectrum associated with a particular molecule, methane. So one carbon and 4 hydrogens. So the spectrum consists of the intensity of the light emitted by this molecule as a function of the wavelength. Now here the wavelength, I've actually plotted the wave, what's called the wave number. So the wave number is obtained by 2 pi divided by the wavelength. So the units, well, the wavelength here was measured in centimeters. So our wave number will have units of inverse centimeters. Pi, remember, is just a number, 3.14159, etc. And so the units of wave number are 1 over centimeters. And these vertical lines here are where the light is, or in this case, the infrared light is emitted by the methane molecule. So it's only emitted here at these very narrow ranges of wavelength that are so narrow that they just appear like a vertical line. And that's why we call them emission lines. In the French is R-A-I-E for emission line, or a line, or a spectral line. You also have absorption spectra that consists of these narrow wavelength ranges, which along which the light is absorbed. But here's our emission spectrum. Consists of regularly interspaced lines, and then a bunch of very closely spaced lines here. This is probably what we call a rotational band. They correspond to the different rotational motions of this molecule. And because this CH4 molecule, it's a simple molecule with 5 atoms, but that's complicated enough that it can vibrate in different ways, and these different emission lines correspond to changes in the quantum state of vibration of this molecule. And because quantum energy is quantized, we get the emission at these specific energy levels, and energy levels correspond to wavelengths in light. I guess I'm saying here that the lines correspond to a transition from one energy state to another through via either the absorption or the emission of a light quanta, a photon of light. When I'm talking about vibrational modes and rotational modes, I'm talking about a molecule. When it's just an atom, then the different energy levels and then therefore the transitions correspond to a change in the electronic configuration of the atom. But the point is we have a spectrum associated with atoms or there's a spectrum associated with each atom, there's a spectrum associated with each molecule, and so we can identify the presence of light of these different atoms and molecules based on the absorption and emission spectra. But there's a problem. There's a problem that held up astronomy and astrophysics for a long time that wasn't really addressed until the 1990s. And so almost 30 years ago now, the problem is that if you're interested in looking at molecules, their absorption and emission spectra are in the infrared or even the microwaves, so millimeter waves, millimeter wavelength waves, and the problem is that the atmosphere has water in it. The atmosphere here on Earth. And this water, the problem is that the water vapor and the ice water in the clouds absorbs strongly in the infrared and millimeter microwave region of the spectrum. And so this water vapor in the atmosphere tends to hide the part of the spectrum that we're looking in to try and identify these molecules by spectroscopy. To make this point a little bit stronger, I've shown the solar spectrum. So this is the light emitted by the sun. So the intensity of the light on the vertical axis versus the wavelength here on the horizontal axis. And in this case, my wavelength now is in nanometers, going from 200 nanometers to 2,500 nanometers. 2,000, so that would be 2.5 micrometers, right? A micron is a millionth of a meter. A nanometer is 10 to the minus 9. For reference purposes, the coronavirus is a tiny little spherical virus, which is about 100 nanometers in diameter. So it would just be off to the left of this axis here, or two coronavirus side by side would be just at this wavelength here. So in the red line, we have the spectrum of light emitted by the sun as observed outside the atmosphere. So you need a telescope just on a satellite outside of most of the Earth's atmosphere. And so hundreds of kilometers above the surface of the Earth. And you might notice the rainbow here, or the colors of the rainbow. That's to show you where the visible part of the spectrum is here on this wave, because color corresponds to wavelength, right? So here about 800 nanometers is red light, and blue light is 500. And we go down in the visible stops around 400 nanometers, and below that is the ultraviolet. So there's still light there, it's just ultraviolet. We can't see it with our naked eye, but some animals, bees, can see in the ultraviolet. And here's the infrared, so with wavelengths longer than 800 nanometers. Anyways, this light at the top of the atmosphere is then transmitted through the atmosphere and partially absorbed. So the result of the spectrum measured at sea level, here in blue, is this line here, and it's lower because of the absorption and scattering in the atmosphere. And I guess my key point is that if we go out here into the infrared, we see strong absorption bands throughout the infrared and microwave band here. And to help make this clear, we have the absorption spectrum now of water shown in green. And we see strong absorption here at near 2000 nanometers, or 2 micrometers. Okay, so that highlights the problem that we're facing. And I should mention I got this image from this website. This problem is mostly due to water vapor, but in principle, ice would also absorb and does absorb microwaves and infrared, but we can get around that, mostly the problem for the ice, by putting our telescopes in very high mountains in very dry regions. But it's hard to get around the water vapor, which is just everywhere in the atmosphere. This held up astronomy and astrophysics greatly until the 1990s, as I mentioned. There was a breakthrough in 1994 when they, for the first time, detected water from a galaxy that was actually 1.5 billion light years from the Milky Way. And they did so by using a radio telescope at very high altitude, almost 3,000 meters here in southern Spain. To really get around this problem, though, of the absorption of infrared radiation in the microwaves in the Earth's atmosphere, you need a telescope in space. And so the space agencies, especially the European Space Agency, got on board with this in the 1990s by launching what's called the ISO, the Infrared Space Observatory, between 1995 and 1998. And it was a tremendous success. They put a telescope in space and basically proved the existence of water and many other molecules. throughout the universe. And so I want to take some time to tell you of some details of this mission. And just making sure I have the darn screen shared. Okay. So the diameter of the telescope was only 60 centimeters, but which is not big for a land-based telescope. It'd be a small telescope here on Earth, but when that's a telescope in space, that can achieve quite a bit. And they had to keep the instruments cold or the telescope itself at 8 Kelvin, and some of the instruments on board were kept at 2 Kelvin. Remember, this is 2 degrees above absolute zero, so these are really cold temperatures. To do so, they needed a liquid helium at to maintain the cold temperatures. And because helium evaporates, then this set a sort of limit on the life span of the mission. It did last longer than it was planned, and so they managed to get 3 years out of it. And they had, I guess I say a spectrometer here, but they actually had 2 spectrometers working to cover the spectral range of wavelengths going from 2 micrometers, so 2,000 nanometers, up to 200 micrometers, so 200,000 nanometers. So to put that a little bit in perspective, 200 micrometers, micro is 10 to the minus 6, so this would be 0.2 millimeters, so that would be 1/5 of a millimeter, right? So 1/5 of the thickness of a centime, approximately. Human hair is about 60 micrometers, depending on the hair. But so that allowed the observation of many absorption lines, and hence the unambiguous detection of molecules, above all molecules, right? Because the atoms are more in the visible part of the spectrum, or the spectrum of atoms are in the visible, and molecules have spectra in the infrared and microwaves. So thanks to this satellite mission in the European Space Agency, astronomers were able to observe the absorption characteristics of, or the spectral absorption lines characteristic of water, among other molecules, but water in the gaseous and solid state, in stars and galaxies, basically throughout the universe. They found, you could summarize the findings by saying they found water in water vapor and solid water ice in stars that are, or near stars that are close to Earth, far from Earth, the big stars, little stars, young stars, old stars. They really found that water is present throughout the universe.